All right, good morning. Okay, let's finish the grading vector first, and then we'll get on to a new topic called directional derivative. Okay. So just have a quick review on directional derivative. If I have a function of two variables, okay, so this is function two variable here, and we all know function two variable means this is a surface. Then calculating the grading vector is essentially calculating, give you a 2D vector here. Okay. 2D vector meaning this is a vector function, essentially it's a function of x and y, and if you plot these vectors, the vectors are all going to be in the xy plane. And we have proved in the previous lecture that this grading vector is going to be perpendicular to the level curves of this f of xy equal to c. Okay? Yeah. So if you have a surface which has certain level curves here, and then del f is perpendicular to the level curve at here, okay? Or perpendicular to a tangent line to the level curve. This is equivalent. Now if you have a function of three variables, we can also calculate grading vector, but that'll give us a 3D vector now. Okay. A 3D vector basically means it's a vector pointing in certain direction in 3D space, and this vector is perpendicular to level surface f of x, y, z equal to c. Now the level surface, when you see f of x, y equal to c, basically that surface, I'm just drawing arbitrary surface here. Then at a certain point on that surface, and then you have your del f maybe pointing certain way, and that del f is perpendicular to this surface at here. Okay, so this is what we also proved the two theories from previous lecture. Okay. Now one more thing, what I want you actually to remember is what's the meaning of grading vector del f. Okay. Now this is something, you know, whenever you finish a class, there's always something that you probably remember for a relatively long time, and this conclusion in here is something that you should remember out of this class. So basically, what does grading vector mean? Very simple, okay. Grading vector del f, it points to the direction of greatest increase in function f. Okay, so that's basically the gist of grading vector, which I will prove to you today. Once we finish the directional derivative, we'll see why that grading vector points to the direction of greatest increase in this function f. Okay. So what this really means is essentially it's a derivative concept. If you change in the direction given by del f, okay, so for example, function f is a function x and y, you can change x, y, right? If you change your x, y, then there will be a change in the function f value. So how do I know that how do I change x and y such that f goes the greatest, the fastest? So the one way to know is you change your x, y in the direction given by the grading vector del f. So if you change your x, y that fashion, that kind of direction, then your function f will increase at the greatest rate. That's basically what grading vector give it to you. Okay. So there's only one topic left here now, which is actually essentially something to do with the theory given over here. Okay. So let's get back to this theory here. Okay, if I have a function f(x, y, z) and its grading vector is given by this, and the conclusion is this grading vector perpendicular to this level surface. Okay. So often in time there will be a question like this. You'll be given a surface. Okay, this is a surface given, and we want to find a tangent plane, okay, to the surface at a point 211. Okay, at a point 211. Okay, so this is not the typical kind of surface we see usually. We see the surface is z equal to f of x, y. Okay. Now this one here is what, if you recall that, we call this an implicit expression because z was not expressed explicitly like this one here. Right? But it's still a surface because if you can always write z squared or z equal to a function of x and y. Okay, so it's still surface. So how do I deal with this kind of question? You can relate back to basically this theory right here. So given this function and its grading vector is this, and then calculate the grading vector. Okay, so grading vector is perpendicular to the surface at a certain point. And in order to find a plane, and we only need two information. One is a point on the plane, the other is a normal vector. Right? So we already have a point already, so the point is over here. So we only need a normal vector to the plane. And according to the theory, grading vector happened to be the candidate because grading vector is perpendicular to the surface at any point. Okay, so what we need is to calculate the grading vector based on this surface that is here. Right? Now, if you look at this surface here, basically you can consider this whole left side here. Let's consider as a w here, or consider it as a function f of x, y, z. So this is your whole left side as a function 3 variables. Then this function f of x, y, z equal to 4. It basically represents is a level surface. Okay, so this is a surface, but it's a level surface. It's a level surface for f of x, y, z. Now let's look at this point here. Right? Let's look at this point. If I substitute this 211 back into this surface given equation, I get 2 squared, 1 squared minus 1 squared. And which happen to be a 4 here. So basically means this point here is on that surface. Okay, so the question given typically when you see find the tangent plane to the surface at this point needs to be on that surface there. Okay, it needs to be on the surface. So this is just a quick verification, but typically the question you don't need to verify that. Okay, so point 211. Okay, is on the surface. Okay, it's on the surface there. So now let's use the formula to calculate the grading vector. So we need the grading vector del f, which is partial f, partial x, partial f over partial y, and partial f over partial z. And this gives us, okay, so here's function here, so 2x, 2y, negative 2z. That's grading vector at any location, and we need a grading vector at the location 211 to construct the normal vector. So del f at 211 plugging x with 2, y with 1, z with 1, we get 4, 2, negative 2. Okay. That's the grading vector, which is basically a perpendicular vector to that surface at that point 2, 1, 1. So the tangent plane, the rest work is the tangent plane, basically you substitute into the plane equation 4, which is the a value, x minus 2 plus 2, y minus 2, x minus 2, y minus what? 1, right? The 1 value. And then negative 2, this is your c value, z minus 1. Okay, so that's your plane equation. A quick simplification, you end up with 2x plus y minus 4z equal to 4. Okay. Okay. So that's the type of question. If you have a surface, then what's the tangent plane for that surface, okay, at a certain point? Let me give you a similar question, but a different kind of surface here. Okay, yeah, this is where I usually find people kind of could get confused here. So given z equal to f of x, y. Right? So let's say x squared plus y squared, for example. Okay. This is a very typical surface we see. It's a function 2 variables. Now, if I want you to calculate, find a tangent plane to z equal to f of x, y, okay, at, let's see, for example, okay, for this question in here. So let me use a general point first, and then a specific point. Let's say at this point, x naught, y naught, and z naught. Okay. So, such as, okay, let's say, can you give me a point on the plane, for example? If I give you x naught as 1, 1, okay, if I give you x naught 1, 1, what will be the z naught value? 2. Good. So that's an example of a point on the surface. So let's say we try to find a plane to this surface at arbitrary point or specific point, okay, like that. Okay. Okay, so if I plot this thing out, you have a paraboloid, and 1, 1, 2 basically means if this is 1, this is 1, okay, and it goes up, so that's basically 2 at here. So this point is the P naught point. Okay. All right. Now, very similar question, but what's not quite the same from the previous example is, so the previous example, given a surface which is an implicit surface, so it's f of x, y, z equal to a constant. Okay, that's exactly the format like this one here, right? But in this example here, okay, the surface says given as z equal to f of x, y, z equal to f of x, y. So what's confusing to some student is, then where is that function f of x, y, z? Right? That's basically, I see sometimes people get confused here. Okay? I mean, when I draw it out, it's still the surface, right? If I draw this out, I can get a different surface, but it's still a surface here. So just the question is, where is that expression f of x, y, z? Okay, essentially. Okay. So you have to actually sometimes kind of to transform the information from one way to another here. When we say we have a function or we have a surface z equal to fxy, now you could consider from a slightly different perspective. For example, here is what I can do. I'll let's say w equal to z minus f of x, y. So I'm redefining a new function w, which is z minus f of x, y. Right. So now this function w, right? This one here, this essentially is, if I look at the whole right side there, that's a function of 3 variables, x, y, z. Right. The way I write could be confusing because I have 2f here, but maybe I'll just write a w here. Okay. So that's a new function, which is a function of 3 variables now, x, y, z. So if we let w equal to 0, if we let w equal to 0, so when you let w equal to 0, what this means is you have a function 3 variable, you're letting that function equal to 0. So you're defining a level surface. So this is basically what we call a level surface here. And this level surface, if you plug in w equal to 0 here, this level surface turned out to be the given surface z equal to f of x, y. So the idea is, whichever surface you're given, so as long as a surface z, whether it's a z equal to f of x, y, or whether it's a surface like this, any piece of surface, is a part of a level surface with certain function 3 variables. So if you think about a surface in 3D space, is a certain surface, you can always think of that surface as part of a level surface of another function. Right? So it's like in the universe, there's always bigger things in the universe here. Right? So this surface is part of a cluster of level surfaces given by this w function. Right? When you let the w equal to 0, you get this surface here. So now things will be easier now. Once you understand this, so we're looking for a tangent plane at this point, or we're looking for this grading vector at that location, perpendicular to this level surface. So how we can do is we basically will follow the same procedure here. So del w equal to partial w over partial x, partial w partial y, partial w partial z. That's the grading vector at that location, and then you can draw basically a tangent plane at that location. Right? That's del w perpendicular to the tangent plane. Okay, so let's take a look at from general to specific now. Here is my general function, any function, before I plug in the actual function f of x, y here. So let's say what's partial w over partial x. And the first term has nothing to do with x. The second term has a function x here, so that's partial f over partial x. Partial w partial y, similarly, partial f over partial y. And then partial w partial z, and that gives us 1. Right, there's 1 here. This is the grading vector for that particular level surface. And then let's plug in the values. What is del w at, for example, right? For so let's go back to our specific question. If the function is x squared plus y squared, then we have negative 2x, negative 2y, and then 1 at here for our function, for our system. So now del w at 1, 1, 2 is negative 2, and 1. Okay. Now we're plugging everything to derive for the tangent plane using the plane equation. So this is your a value, this is a b value, this is a c value, and this is your x naught, y naught, z naught. So negative 2 times x minus 1 plus negative 2 times y minus 1, and then plus 1 times z minus 2. Okay. So a little bit simplification, you get negative 2x, positive 2, positive 2, so 4 minus 2 is 2. So negative 2x minus 2y plus z, and then equal to negative 2. Okay. That's the solution for this one here. So even though this question didn't give you the function 3 variables directly, but you should write it into the function 3 variables format, and then you calculate the grading vector. Then you can apply the points and apply the plane equation, and you get the tangent plane. Okay, yeah. So that's the idea of the grading vectors here. Okay, so what you need to establish at this point is what is grading vector, and if you're giving a surface, right? If you're given a surface, so what kind of grading vector you basically require to calculate here? Are you required to calculate the 2D vector, or are you required to calculate the 3D vector? The 2D vector is in the xy plane, of course, and 2D in the xyz plane pointing to a certain direction. Okay. And if you're looking for it here is looking for is a tangent plane, then you got to be calculating that for that 3D vector here, right? Del w or f of xyz. Okay. Any questions so far on the grading vectors? Yeah. Okay. So I want you to memorize a couple things, right? One thing I want you to memorize, at least for the rest of the term, or for the rest of the year, is what does grading vector mean, right? What does grading vector give it to you? That's a very common question, right? All right, so now let's get on to the new topic, okay, directional derivative. This is a very simple formula. Okay, so I can tell you is directional derivative. The results is very simple. Okay, in terms of computation, but I'm gonna have to spend some time actually trying to explain what directional derivative means here. Okay, and then we'll relate back to the idea, the concept of grading vector. So let's start from very beginning. Okay, very simple here. Let's say consider the single variable function y equal to x, f of x here. Now this is the first, the case 1 is what you have learned in first year. You calculate okay, you calculate the derivative df over dx, and according to the formula, okay, so here is the limit that's involved for this derivative. So we get essentially a slope concept, okay, or rate of change of this function in terms of this x here. So now let me explain this a little bit here, but I'm going to explain this in a slightly different perspective here. Okay, so I'll use, let's say, a function of y equal to x squared for illustration. Then that gives us this slope is 2x, as we all know. Okay. So if I draw this out here, okay, here is the function at y equal to x squared. All right, and then if you're going to calculate, okay, the slope like this, then what happens is, okay, if this is x value and this is x plus delta x, okay, then we can get a slope, okay, right here. So df over dx. Okay. So that's the idea of a slope concept, or using a line to represent part of that curve around the x value here. Now, but what I wanted to understand here is this is a new perspective. So this essentially referring to x goes to x plus delta x. Okay, so this essentially means x goes from x to x plus delta x. It's like you're walking from this initial location to the direction, and this direction here is a positive I hat direction. Right? This is x-axis direction. So you change your x in the direction of I hat by a small quantity delta x. And this change resulted in a slope of 2x at here. If I plug in x, for example, if x equal to 1, then my k equal to 2. So we all know if k equal to 2 basically means at this location, if you go from x slightly to the right, okay, which is the I hat direction, then you would expect that because it's a positive number, then you would expect there will be an increase in this function f, right? Okay, yeah. So now I'm gonna change this a little bit here. Okay, I'll use the same equation and here. I use the same equation, but this time what I'm gonna do is, okay, I'll calculate the limits in a different way. I'll calculate the limits like this. Okay, yeah. So you see the difference this time when calculating limits now. So previously what did I do? It's x plus delta x. Right. Now this time what did I do? X minus delta x. So the way it changes here basically, previously we're walking in the I hat positive x-axis direction by a delta x. And this time, I'm actually walking change this x in a completely different direction, which is the opposite direction, the negative x-axis direction. Okay, yeah. Then what happened to this results then, right? You can apply if this is a function y equal to x squared. Okay, you can apply the basically the limit concept here. And also apply basically the Taylor series, and then you'll get results for this limit to be negative 2x at here. So you'll get a negative 2x. Okay. So basically plugging x minus delta x into here, plugging x over here. Okay, you end up with this expression, and then get rid of a 1 delta x here, and you get a negative 2x when delta x equal to 0. So now what this means is if x equal to 1, then if this is k1 here, then this slope at here becomes what? Negative 2. Right? So negative 2 here. So you see, I'm not changing the function, the same function, y equal to x squared. So if I plot this thing out here, okay, it's the same function, same curve, okay, and we're talking about the same point, for example, at x equal to 1, right? Same point. Okay. But previously, when you move your x to the positive x-axis direction by delta x, we have a positive slope too, meaning there will be an increase in the function f. But this time, if I change the x, okay, from 1 to an opposite direction, which is negative I hat direction, okay, then the slope, okay, you get the same line here basically, okay, then the slope becomes negative 2 now, becomes negative 2. And negative 2 actually makes sense, right? Because why? You see, if I go from 1 to the left, what's the resulting function value y here? It must be what? It must be decreasing, right? And that conforms with this negative slope right here. So negative slope basically means there will be a decrease in the function f as you're moving from x equal to 1 to the negative I hat direction. All right? Yeah. So now this essentially, I'm introducing it here is a directional concept. Okay, it's a directional concept, and I'm gonna explain this a little bit more here because this is the whole idea of a directional derivative. So I'm gonna draw this graph, okay, in a 3D scenario here. This is y, this is x, okay. And now here is my y equal to x squared, but I will, okay, draw it, okay, using two colors, okay, for the two sides of the curve. Okay, so this is still the y equal to x squared. Okay. Yeah. Okay, so now here's what happens here. If I'm going to change the x, okay, in the positive x-axis direction, so this is going to be, I'm using a notation here. Here's the positive displacement direction. So positive displacement direction. You're changing in the positive axis x direction here. All right? Yeah. Then we'll establish this new curve, okay, in a sense, okay, in a slightly different sense now. Okay, so I'm going to erase this one here. Okay, just basically make it a parallel here. So I'm going to establish this curve, okay, within y and the positive displacement direction. So not in the positive, not in the x-axis direction, x-axis anymore. Okay, establish a coordinate system between y and the positive displacement. You still use the right-hand rule. So when you establish new coordinate system, you know, your positive still conforms with this right-hand rule here. So it's not going to be this side here, it's still going to be this side here, right? So now I can redraw this graph right here. Then essentially if I redraw this one in this perspective, it's like you're looking from, you know, from this direction here, right? You're looking from this side of the plane. If you look from this side of the plane, guess what? You will see this y here, this positive displacement s at here, right? Yeah. Then this curve essentially means you have red here, and then what? Green here. Okay? Yeah, that's how you see when you're looking from this perspective. When you look at this perspective, you see here, if I go along the positive s, positive displacement direction, I get essentially a positive slope. I get an increase in that function, right, at x equal to 1, which is exactly what we expecting here. Okay? Yeah. And now let's look at the other scenario. So the other scenario is, this is y, this is x. Okay, so you have exactly the same curve. Okay, you have exactly the same curve. But if you recall that, but this time we're moving in which direction? In the negative x-axis direction, right? Or in the negative I hat direction. But I will call that as the positive displacement direction. So that's basically the directional concept. So I will call this is the positive displacement direction. It's different from the positive displacement from the previous case now, right? So now if I wanted to establish, very similarly like the previous case, between y and positive s. Okay, so if I want to establish this connection between y and positive x, s, okay, as the new coordinate system, so guess which direction or which perspective we should look at this curve now? Are we supposed to look at from this perspective? If I want to establish this connection, right, this relationship, if you look this way here, the S pointing that way, right? So which direction? The opposite direction here. Okay? It's a very bad eye here. Okay? Yeah. Does that make sense? So if I look at from this direction, okay, so tell me if I want to draw this curve properly, okay, which side is red, which side is green? The left side is green. And the right side is red. Okay, the right side is red. Does that make sense? Yeah. So you see here, you still have to relate back to this here. So where is x equal to 1? x1 is here, right? This is where x1. So I'm talking about the same location for the same reference here. So when you walk from x equal to 1 to the negative x-axis or to this positive displacement direction, it resulted in a decrease in the function f. So let's take a look at here. Where is x equal to 1? X equal to 1 here. So basically, right, it's here. Okay, as we're walking the positive displacement, that's the positive displacement, right? And you can see here, you get essentially a negative slope at here. Okay, you got a negative slope. Okay. So this is very different from the regular slope concept that you learned in first year. So this is more or less introducing a directional concept. Okay. As you walk in a certain direction, you get a slope. You walk in another direction, you get another slope. Okay. And for 2D, it's actually quite simple. You only have two directions, either positive x-axis direction or either negative x-axis direction. So you either get a positive slope or you get a negative slope, basically. Okay? Yeah. So I'm going to write it as sort of a new concept in terms of slope now. So what is the slope now? Slope is between this vertical axis, okay, that's vertical axis y, and I'm not going to use the x-axis anymore, so I'm going to use this positive displacement. Okay, so this positive displacement. So we're talking about a new concept here. Is we're looking at the slope is between the vertical axis, okay, whatever that z-axis, could be y-axis, later the z-axis, and then this positive displacement direction. Okay. You establish coordinate system between the vertical axis and the positive displacement axis. There got to be a curve, okay, that you can draw within this new coordinate system, and then you look at the slope of that curve, okay, within this new system, and that's basically give us the so-called directional derivative here. Okay, okay. So let's look at a more general case now. Okay, so more general case. But before even we go on to more general case, and let's maybe recall here the partial derivative concept. Any questions so far? Okay. Is it clear about the derivative concept, the slope concept? Yeah. Let's consider again function two variables, which is surface, and we have learned partial derivative, and the concept of partial derivative is given by this definition. So here is a partial derivative definition, partial f over partial x. Okay. Now, and I want you again to relate back to this slope concept here. Okay, slope concept by just looking at this expression here. Partial derivative here. So what happens is you're looking at rate of change for this f here. So rate of change rate of change in the function f, okay, in this function f, in what direction? So if you look at this way here, x changes from x to x plus delta x, and y are being kept unchanged. So if you consider your movement, if this is initially x, y, then you're moving from the initial point to where? To x plus delta x, y. And in other words, if this is initial point here, you're not changing y, you're only moving this point to the positive x-axis direction. So if this is x, y, and this is your x plus delta x and y, right? Okay. So partial derivative, partial f over partial x, basically means give you a slope or rate of change in this function f. Okay. In the positive, okay, in this positive x-axis, I should probably write positive down here. Okay, in the positive x-axis direction. Okay. And positive x-axis is positive I hat. So you can see the partial derivative, right, is a special directional derivative concept, because it's a special direction. It's I hat direction. Okay. If you move in that direction, then you get the partial derivative. All right. So all I'm looking now is all very special cases. So now the big question here is this. So the big question is, so what about an arbitrary direction? So what about an arbitrary direction? So I will use this function two variables to illustrate this idea here, okay? So let's consider function in two variables here. Here's a function z equal to f of x, y. And I'll draw something here. It could be a little bit complicated, and so bear with me in terms of the drawing. Okay, here is a function that z equal to f of x, y. It's an arbitrary surface. So I'm going to start from an initial point, let's say P at here. Let's call it P naught. X naught, Y naught. So here is initial point P naught. And then from this P naught, okay, so let's consider if you have a P naught here, then you're going to move this P naught, okay, to a different location. Okay, to a different location. So we're going to move this P naught, for example, to this direction given by a U hat. Okay. So you can consider, let's say, you are the person down here. Okay, so you're maybe walking in, you're confined within this XY plane here. Okay, so you're not moving anywhere else. You're confined within this XY plane. Right now, this little person is going to move in the U hat direction. So as this person is moving, there is another guy, okay, sitting on the top of the surface. So for this person here, okay, and this person initially at what point? X naught, Y naught, and then what? What's the Z value? That's right. Okay, so that's initially this guy's location. Okay? Okay. So now let's start to move this person A, and this is person B here. Okay. Once you start to move the person A, and the B will be moving at the same time. Okay, it's like they're confined by a tight string. But then B also is confined to the surface at here. Right. So if you're moving A to the direction of U hat, okay, so let's exaggerate the situation here. Let's say I'm gonna move the A always in that direction of U hat. Is that okay? Right. So that basically A is gonna walk in the direction, okay, the straight line at here. So this is a line equation, right? Yeah. Then that person B, as you can imagine, okay, as the person A is walking along the line, then the person B will inevitably track out a what? A certain curve along that surface S. Okay, surface. That make sense? Yeah. So that it's like the person B is climbing the hill, and whenever you command the certain direction, and he's going to have to climb in a certain direction. Okay. So that's what happened to the B there. If you keep going along this straight line here, then the person B eventually will go along a certain curve like this. Or you could also think of it like this. If this is a straight line, it's tracking. Then whenever you extend that straight line, if you recall that, the straight line can also always be extended as what? As a plane, right? And this plane will cut through the surface to yield this green curve here on the surface. Okay, yeah. So here's a question now. Essentially, if you go from x naught, y naught in the u hat direction, and that's what we call the positive displacement direction, right? If you go from here to the u hat direction, then what will be the slope, or what will be the rate of a change for the person B, okay, as it going along that green curve there? Right? That's essentially the question at here. Let's say if I call this is a curve C, okay, if I call this green curve is a C at here. Okay. So the idea is as P naught, okay, moving in U hat, okay, direction. Okay. So what is the rate of change? What is the rate of change for the person B on curve C? Okay, on the curve C. So that's basically the directional derivative concept, and this is the idea what we call directional derivative. Okay. Yeah. Now, I actually simplified the situation quite a bit, right? Because we have simplified this one here by looking at essentially, if you keep walking this direction, it's a straight line, and that straight line, it's like a plane here cutting through that surface to yield this green curve C. Okay? And technically speaking, right, let's say if this is x naught, y naught location, and that's the B location here, if I'm interested in the rate of change, so technically what I could do is what? I could just plot a tangent line at that B location. It's not a very nice plot, but I could just plot the tangent line at that B location, and then I will look at the slope given by that tangent line. And that slope value will give us this so-called rate of change of this person B on the curve C here. That makes sense, right? Yeah. Okay. So how do we look at this situation, then, right? Yeah. And if I for this particular case here, if I use in my Lee language here, slope is between a vertical axis and the positive displacement direction. So if I go back to this specific situation right here, okay, what is the positive axis and vertical axis in this case? Should use the green. Should use this one here. In this case, what's my positive vertical axis? So the Z, right? The Z here, okay. And what's my horizontal axis? According to definition, the horizontal axis is what? The positive displacement. So here's the positive displacement. But in this case, the positive displacement is given by what? Given by the u hat. So basically, you have this u hat direction. Okay. Okay. Now I established this coordinate system now, and then if I wanted to plot that curve C, plot this curve C into this coordinate system. Okay. So I want to plot it into the system. Guess which direction should I project here, or which direction should I look at it? Should I look at it from which side here? Right. Which side will give me the right perspective for Z and positive S? The left or the right? The right, right? Yeah. So only when you look from this direction here, here's a positive S, here's a positive Z axis, and then the C curve is this, so you can draw the C curve as whatever it should be. Okay? Yeah.
Wouldn't it be the left to have your positive u go to the right?
Oh yeah, of course, yes, sorry. Who said this right here? This side, my friends. I draw a bigger eye here. So, should be this side here, because this side will give you the right perspective. Does that make sense? Yeah. Okay. So then you can draw the curve out like this, okay, as a C here. Okay. And once you draw this out, okay, and then you can nail down the actual location. Let's see, I don't know what is it, but maybe it's the P naught here. Right? This is the P naught. Okay. Maybe P naught is somewhere here. Okay. And then you can draw the slope at that location. Okay. And in this case, as you go along this direction, and then the B is going up, so you have a positive slope, right? The way I draw here. Okay. If you draw it correctly from the perspective point of view, then you should have a positive slope as you're moving in the positive u hat direction. Okay. So that's how you can interpret. Okay, that's basically graphically how you can interpret this idea of a directional derivative. Is that clear? Yeah. So whenever you walk in a certain direction, there will be a rate of change, right? There will be a rate of change. And next we're going to see at a certain direction, a special direction, you get a maximum rate of change, basically. Okay. And it happened to be what? What direction will give you the maximum rate of change? Grading vector. Excellent, right? Yeah. So I'll come to that very shortly here. Okay. Okay. So I hope you understand what directional derivative means now. Okay. And then let's look at the computation of directional derivative. Okay. It's also very simple, as you're going to see. So I will write down the temporarily the u hat direction here. Okay. So let's assuming the positive u hat is given by a I hat plus b g hat. Okay. So the guy A is walking along the u hat direction. Okay. And then starting from initial point x naught, y naught. This is your line basically, right? If you recall that, okay, if I wanted to find the line equation L at here, then which is what? line equation require a point on the line and a parallel vector to the line. So this is your A here. Let's use the parameter S, which is the positive. This is the displacement S here. And Y is equal to Y naught plus A plus B times S. So that's your line equation here, right? Okay. I'm going to use this line equation actually to prove the formula for the directional derivative. Okay. So let's get back to the directional derivative concept again here. Okay. We're talking about the rate of change of this curve C as you're moving in the positive S at here. Now, if you recall, this C is not a special C. This C is still on that surface F here. Okay, so it's still on the surface Z equal to F. So when we're talking about the rate of change in the curve C, we're actually talking about what? The rate of change what? The function F. Okay, so C is basically part of the function F at here. So when you say rate of change of the person B on the curve C, it's equivalent to say the rate of change of the function F as P is moving to a certain direction. Now, we typically, when we, let's say, df over dx, meaning what? The rate of change of f in the positive x-axis direction. That's what df over dx means. Now, if this time I wanted to see what's the rate of change f in the positive displacement direction. So this is the notation of directional derivative. So basically, what does this equal to? If you move in the positive displacement s, okay, a little bit, and how does that result in the change in the function f? That's df over ds. Okay, notation-wise, is it clear? Yeah. So I will give you a formula for df over ds now, and but I will write down the formal definition for the directional derivative first. Okay. So the derivative of f, okay, at a certain point, okay, at a certain point in the direction, okay, given by, let's say, u hat, okay, equal to a I hat b j hat, is denoted as df over ds in the u hat direction at p naught. Okay. So this is what we see a little bit more here in terms of the notation wise. All good? So you can see, so what's the rate of change of the function f when you're moving in the positive displacement given by u hat direction at a certain point p naught? If I wanted to relate to the limit concept, so we have a very similar formula, okay, using the limits. And this is the idea. So you're initially at x and y. Okay. You're initially at xy location, and now we're going to move in the direction given by u hat. Okay, given by u hat. So what happens is we move in the x direction by a little bit, a times h. Move in the b times h. So h is a very small value. Okay, h is a very small value. So you basically give a and b a little nudge, and that h is the quantity you're nudging it. Okay, yeah. And now we let h go to 0. Okay, go to 0 here. And you see, this is exactly the kind of a limit concept for a function of single variables, right? Yeah. So x is changing by a little bit, AH, y is changing by a little bit, BH. So altogether it's in the U hat direction. Okay. Now if you have a certain function, you can always apply this limit formula to derive for the directional derivative. Okay, that's always an alternative way of doing it. But we have a better formula to calculate this directional derivative. Okay, and this formula is what I want you to remember. Okay, so this is your del f df over ds, okay, in the u hat direction. The formula is del f dot u hat. Okay, so del f dot u hat. That's the formula for directional derivative. Very simple, right? You can see, how do you calculate directional derivative? So I want you to spend 1 minute. You can write 10 times, even more than 10 times this. You don't need to remember for the rest of the term at least anymore, right? So you need to calculate dot product between the first one is gradient vector, and the second one is the unit vector, which is pointing to the direction you're moving or you're changing. Okay? So it's simple as that to get the directional derivative. And I'll give you a simple proof at it here, okay, as to how this formula is derived. And this is what we're looking at. So df over ds in the u hat direction. Yeah. So you can, if I go back a little bit here, here's my u hat direction. So we're moving basically along this line here, right? We're moving along this line with this s as the variable, the displacement. Okay. Then I'm gonna apply the chain rule right here. So df over ds equal to partial f over partial x and dx over ds, and plus partial f over partial y dy over ds. Okay. It's chain rule. Now if you have the function f, then you will be able to calculate the partial derivative. But we don't have the function f, so we'll keep the partial derivative here. And dx over ds, so x and y are moving in that straight line direction, L, which is given by the line equation. So you can see dx over ds equal to what? A value. It's a function single variable, so dx over ds give you the a value here. Let's give you the a here. And then dy over ds give you the b value. So altogether, you can write this whole thing in a vector dot product format. And the first term is your gradient. The second term is the u hat direction. So together, you get this simple formula here for directional derivative. Okay. Yeah. So let's take a look at a couple of examples here. Okay. A very simple one here, just to get a hand of how this computation look like, given a specific question. Alright, so here's a function f, and I want you to calculate the directional derivative at 2, 0 in the direction v equal to 3i hat minus 4g hat. Okay. Alright, so let's look at the formula here. We're going to stick to the formula exactly here, okay? Yeah, so what do I need to do? I need to calculate the gradient vector and I need to calculate the gradient vector first, basically. So del f, so here's your function f, del f partial x, partial f partial y. Again, you have to brush up on the partial derivative concept if you want. The first term, e to the power y, partial, treat y as a constant. Treat y as a constant here, so negative sine xy, then times what? Y. Okay. Second term, respect to the y, you treat x as a constant, and then you get x e to the power y minus x sine xy. That's the gradient vector for this multivariable function. Okay, any questions so far? So good? Okay. So now we're looking at is the directional derivative at this point in this direction. And I'm going to calculate the gradient vector at this 2, 0 point. Okay. So x equal to 0, y equal to x equal to 2, y equal to 0. Plugging here, you get 1 minus 0, and then 2 minus 0, so 1, 2. That's the gradient vector at that location. Now let's apply the formula now. df over ds, okay, in the direction v given by v here. So the formula here, if you recall that, requires what? If you look at the formula here, requires u hat, which is a unit vector. Okay, so this is a unit vector here. It's not an arbitrary vector. It has to be a unit vector. But this question is given by v, which is that a unit vector? It's not a unit vector here, right? So you need a v hat at here. Okay? So I already calculated the first term, so del f, maybe I'll just write it down the whole thing here. So del f at p naught dot v hat, which is 1, 2, okay, dot v hat. So normalize the v into unit vector v hat. So 3 square plus 4 square and 25 square root is 5. 1 over 5, 3 negative 4. That's the unit vector. And then you calculate dot product as it is. So 3 over 5 minus 8 over 5 equal to negative 1. Okay, good. Yeah. So very simple calculation in terms of usage of this directional derivative formula. Okay. Okay, so let me ask you another question. Okay, and I don't need you to calculate. Just tell me the answer. Okay. If I give you a function z equal to f of x, y, can you tell me what is the directional derivative in the I hat direction? Anybody? How's it?
It would be a partial derivative with respect to x, because that's multiplied by 1, and the partial derivative with respect to y is multiplied by 0.
Exactly. Right. So this will give you partial f over partial x. Okay. Yes?
I don't really understand that notation. So df over ds bracket what exactly does it mean?
So this means what is the directional derivative for the function f in the I hat direction?
So I hat is a f, or
Yeah.
I hat is the u.
That's right.
Okay.
Yeah. It's a u hat, right?
Oh.
It's the positive displacement direction. Yeah. And in this case here, I hat is positive x-axis direction. So when you're moving in the I hat direction, then you're changing x but keeping y as constant. That's exactly the concept partial derivative f over x. Okay. Good? Yeah. So you can verify though, huh? You can always verify del f dot I hat. You'll get exactly like this. Because you have f here, you know, and you dot I hat. Okay, so let's use the rest of the time just to look at the properties of directional derivative. Okay, properties of directional derivative. The property of a directional derivative are resulted directly from the formula, from the formula here. This is the formula for directional derivative. It's a dot product. Okay. So you have a vector, which is a gradient vector. You have the unit vector, which is the direction of changing. Now, if I consider purely from vector point of view, okay, so that's two vectors, right? That's two vectors, and with a certain angle in between, right? In general. So then, according to the dot product formula, okay, you can write it like that. So del f times the magnitude del f multiplied by magnitude u hat, and then multiplied by cosine theta. And we can make a simplification. What's the magnitude of u hat? 1, right? So that term is gone. Then you give us del f times cosine theta. Okay, times cosine theta. So now you can see the directional derivative, the value, right? The value of the derivative is related to what? Related to the magnitude of the gradient vector and cosine theta. The theta value is between del f and u hat. Okay. So I can maybe illustrate this a little bit here. If this is my function f here, okay, right? Let's consider function two variables. Then del f, okay, is going to be, let's say, a gradient vector in the xy plane. Okay, here is del f. If this is a point we're interested, okay, so here's the del f. If you calculate that at that point, and u hat is certain direction. So u hat is certain direction like that. And there's the angle theta, right? It's angle theta. Then the directional derivative basically is del f magnitude times the cosine theta. Okay. All right. So what does that mean, right? So let's take a look at a couple of special cases at it here. Okay? A couple of special cases. Let's look at the first case. What happened when theta equal to 0 degree? 0 degree here. Sorry? Just del f, exactly. So if I plug in 0 at it here, and we get cosine 0 equal to 1, right? Oh, by the way, actually, I got some question during exam, what sine pi is, what sine 0 is, what a cosine 0 is, like that kind of question, okay? So I got to make my expectation clear. I don't expect you to remember all the trigonometry formula, but as a student, as a future professional engineers, you should make some effort to remember some of the very special sine, cosine values. Right? You know what? Yes. What sine pi? What sine 0? Write down what? Sorry. This is the point I'm trying to making at it here. you should try to make effort to remember the special values of sine angles or cosine angles. For example, what's the sine 30 degree? 1/2, right? Yeah. What's the sine 90 degree? Yeah. This is the effort I'm trying to expect you to remember, because you know why? I'll tell you. Because we had the industry advisory committee meetings regularly. One of the feedback from industry is they want students to have some common sense, not just always rely on calculators. So the civil engineer, the guy said, I want you to build, I don't know, an 8 feet by 6 feet of, dig a hole or something, right? So I have a student trying to figure out, so how long is 8 feet to 6 feet? So that type of a common sense, and it says, well, as an engineer, you should probably roughly know how long that thing, kind of things. So I think that's similar. If I want you to calculate certain values involving sine degrees, okay? You don't necessarily have to always bring out the calculator to do the calculation, right? And I'll be honest, you could embarrass yourself if you do that, every time using the calculator, right? So that's my expectation. I always lower my expectation actually, because in my final exam I do give you some of the special values, but when I teach my own kids, I force them try to remember some of these things here. There are ways to trying to help you remember these things, right? Yeah. So anyway, so we're wandering off a little bit here, okay? So theta, cosine theta 0 equal to 1 right here, okay? Yeah. Then, which means basically the df over ds, okay? We got here, we got a maximum value, okay? We got a maximum value for the results, which is the magnitude of this grading vector, okay? The magnitude grading vector here. Okay. So now what it means is, when the grading vector is in the same direction of u hat, or when u hat is the same direction of the grading vector, you get the maximum directional derivative, right? So remember what the directional derivative means. It's the rate of a change of this function f when you're moving in that direction, right? So now you get the maximum rate of a change for this function f as you're moving in that direction. But in this case here, which direction are we moving in the first case? Which direction are we moving here? What direction are we moving in this direction when theta equal to 0? Which direction? With theta equal to 0, what direction we're moving here? Del f, right? In the del f direction. So if you recall that conclusion, I have wanted you to remember at the beginning of the lecture. What does the del f give you? The direction of the greatest increase in the function f. And that's actually basically a proof at here. Okay? Yeah. So in this case, u hat is in the same direction as del f. Okay. So let's look at another special case. Now what happened when theta equal to pi? So your cosine pi, and what does cosine pi equal to? -1. Okay. So if this is pi, then u hat is which direction? U hat is that opposite direction as the del f. In this particular case, your df over ds, okay, in that direction u hat is what? You get a minimum value, which is negative this magnitude del f. So if you move in the opposite direction, of the grading vector, then you get the minimum value. So if I say, if you move in the grading vector direction, you get the greatest increase in the function f. Then what would be the proper words? If I move in the opposite direction of the grading vector, I should get what? Instead of greatest increase, I get the greatest decrease, right, in the function f. Okay. This is actually very important concept. In mathematics, there is a branch called optimization. Basically, it's called the gradient descent approach. It's a numerical approach. It's a gradient descent. So if you're on the slope hill, how do I go as fast as possible to the bottom of the hill, right? So that you use this, basically this concept here. So last one here, sorry, just let me finish this one. So what about theta equal to pi over 2? What's cosine pi over 2? It's a 0 degree, then a 0. So it basically means you get df over ds in the u hat equal to 0. So what does pi over 2 means? Means u hat is what? Perpendicular to this grading vector. Okay. Now, this essentially means you're walking, if you walk in the u hat, which is perpendicular to the u hat, you get a 0 value for the directional derivative. So what does 0 value means? Huh? What does derivative equal to 0 means?
No slope.
No slope, right? Meaning you're walking in a constant leveled altitude, right? So if you walk in this direction, it's constant altitude there, okay? Yeah. No slope change, right? So we'll look at a couple examples next lecture here, okay? Yeah. Any questions so far? Okay. Thank you.